Okay, finally. The last topic in section 7.5 is topic 7, which is about even and odd functions. Now, even and odd functions, that's something you talked about in Math 171. So let's do just a quick review of what even and odd functions are. So a function is even if f of negative x equals f of x. Okay, so what that kind of translates to is we have opposite inputs yield equal outputs. So opposite inputs yield equal outputs. So basically, you evaluate a function for opposite values, you get the same result back. And so the classic example of an even function is y equals x squared, which we have shown here. So when you're dealing with an even function, it is symmetric about the y-axis, okay? So symmetry over the y-axis. Now, on the flip side, odd functions, we have a situation where a function is odd if f of negative x equals negative f of x. So opposite inputs yields opposite outputs. So you take a function, you evaluate it for opposite values, and you're going to get opposite values out, okay? And the classic example of that is y equals x to the third. So y equals x squared y equals x to the third. And what we notice about odd functions is they're symmetric about the origin, okay? So you've got values here that show you, not values, but you have graphs here that show you a classic example of an even function and a classic example of an odd function. We have the idea that even functions, you have equal or opposite inputs yield equal outputs. For odd functions, opposite inputs yield opposite outputs. And I have that typed and written, so hopefully hopefully you didn't miss that part. Okay, so now when it comes to even and odd functions when trigonometric functions are involved, we do have a situation where all of the trigonometric functions fall into one of those two categories, okay? So in order to prove this to ourselves, we have to start with sine and cosine, okay? And a lot of times you're going to see this a lot where if we can understand something about sine and cosine, we can let that follow through to the remaining four trigonometric functions. So in this case, we're going to say f, and I'm going to write it out here just so it's easier to see. We're going to say f of theta equals cosine of theta. And we're going to say, was it g of theta equals sine of theta. So we have these two functions, sine and cosine. Okay, now we know when it comes to ordered pairs, when we're on the unit circle, okay, if we're very specifically on the unit circle, we know that any point on the unit circle is going to have some x, y ordered pair assigned to it. Well, we know that when we're dealing with the trig functions, as long as we're on the unit circle, x corresponds to cosine of theta and y corresponds to sine of theta. Okay, we know this. We've talked about it several times. So what we have down here is a unit circle. Okay, and we have drawn two angles. Okay, we have drawn, and I'm going to do them in different colors so you can like really see. We have drawn a positive angle theta. Okay, so we've got theta right here. And then I'll do blue for the negative. And then we've drawn the exact same angle theta, but negative theta. So they represent the same amount. One's positive, one's negative. Okay, so we have our negative theta down here. What we want to do is look at the points, the ordered pairs on the unit circle, those ratios or those output values. So right here, the point, let me do that actually in red. The point on our unit circle is x, y. And then for that negative theta, we came down here and we have the point on our unit circle, which is x negative y. Okay, so we need to use this idea right here to prove to ourselves if sine and cosine are even and odd. Even or odd, I guess I should say. So example 9 says, use the circle, unit circle above to determine if sine and cosine are even or odd. Well, let's talk about f of negative theta. So f we decided was cosine, okay? So if we're looking at cosine, remember, we're really looking at the x coordinate. Let me move my face. My face is in my way. So we're really looking at the x coordinate, and for sine, we're really looking at the y coordinate. Well, when we look at f of theta, we get x, right? We get our x right here. When we look at f of negative theta, we also get x. So what we can say is f of negative theta equals f of theta. f of theta equals x, f of negative theta equals x. So we have opposite inputs equal outputs. Okay, so when we evaluated cosine at theta and negative theta, we got the exact same output value of just positive x. Okay, so for that reason, we would say that cosine is even. Okay, so we can now say verifying using this picture and evaluating cosine at positive theta and then again at negative theta, we get the exact same output value, which is positive x. Now, g of x, or g of theta rather, was sine. Okay, so let's look at sine. Now, we know that when we're on the unit circle, sine is going to correspond to the y coordinate of those ordered pairs on the unit circle. So when we evaluate g of theta, so g of theta equals y. Okay, we have that right here. Now, when we go down here and we evaluate the blue angle, which is negative theta, we find that g of negative theta is now negative y. So we had that g of negative theta equals negative g of theta. Okay, so what we had here was opposite inputs. So we had positive theta and negative theta, opposite inputs, and the outputs were y and negative y. So let me actually write this a little bit different so it's a little easier to see. So we have that g of theta equals y, g of negative theta equals negative y. So I would say g of negative theta equals negative g of theta. So we have opposite inputs, opposite outputs. So we would say that sine is odd. Okay, so what you need to remember is cosine is even, sine is odd, and if you can remember that, we can figure out the others. Okay, so that's what we're actually going to do in example 10. Yeah. So example 10, we're going to look at the remaining four trig functions. We're going to use identities to determine if they're even or odd. Okay, my pen is squeaking in a really weird way, and it's giving me chills. I hope you all can't hear it. Okay, so example 10 says determine if the following trig functions are even or odd, justify your answers. Well, tangent, okay? So we know that tangent is really sine over cosine, okay? So if we wanted to find tangent of negative theta, that would be sine of negative theta equals cosine of negative theta. Well, since sine we decided is odd, that tells me that sine of negative theta equals negative sine of theta. And since cosine was even, that tells me that cosine of negative theta equals cosine of positive, or just positive cosine of theta. So we end up getting that tangent of negative theta equals negative tangent of theta, because now we have this ratio where we have a negative divided by a positive. So this tells me that tangent is also odd because we have a sign change, okay? Now, if we're looking at secant, we know that secant is the reciprocal of cosine, okay? So secant is 1 over cosine of theta. So remember that. So if I were to evaluate secant for negative theta, that would tell me I have 1 over cosine of negative theta. Well, we know from previously that cosine is even. So that tells me cosine of negative theta is equal to positive cosine of theta. So I just get cosine of theta. So secant of negative theta equals just secant of theta. So this equals secant of theta. So we would say that secant is even. Okay. Now let's do the same thing for cosecant and cotangent. Okay, cosecant we know is the reciprocal of sine. So that's 1 over sine of theta. So let's now evaluate this for negative theta. So cosecant of negative theta is 1 over sine of negative theta. Well, we know that sine is odd. So that tells me sine of negative theta equals negative sine of theta. So this is 1 over negative sine of theta. So now I have a sign change, which tells me cosecant of negative theta equals negative cosecant of theta. So cosecant is odd, okay? Now, finally, we have cotangent. We know cotangent is the reciprocal of tangent. So that tells me it's cosine theta over sine theta. So let's evaluate cotangent for cotangent of negative theta. So cotangent of negative theta equals cosine of negative theta over sine of negative theta. Well, we know cosine is even, so that tells me that cosine of negative theta equals positive cosine of theta. And we know that sine is odd, so that tells me sine of negative theta equals negative sine of theta. So we have a sign change now, so this is no longer positive, so we get that cotangent of negative theta equals negative cotangent of theta. So we would say that cotangent is odd. Okay, so when it comes to the 6 trigonometric functions, they're all odd except for cosine and secant. So they're all odd except cosine and its reciprocal secant. Okay. Now let's look at a couple of examples of how we can use this even or odd aspect of these functions. So in example 11, it says find the exact value of each of the following. Okay. Well, if we have cosine of negative 60, we know that cosine is even. So that tells me cosine of negative theta equals just cosine of theta. So cosine of negative 60 just equals cosine of positive 60. And if we go to a unit circle, hopefully you're getting to the point where you're remembering some of the values on the unit circle, but it's brand new to us, so we can go and we can peek at a unit circle. So let's look at a unit circle. We're looking for cosine of 60 degrees. Whoa, that's not what I want. Let's find a different one. This is what I want. Okay, so if we're looking for cosine of 60 degrees, imagine drawing an angle. We've got our vertex, our initial side, and we want to go 60 degrees. So we intersect the unit circle right here. Cosine is the x-coordinate of that point, so we would say cosine is just positive 1/2. Okay? So cosine of negative 60 is equal to cosine positive 60, which equals 1/2. Okay? Now we have sine of negative 390. So we've got a couple of things happening here. First of all, let's deal with the even odd aspect of this. So I know that sine is odd, which means if I take sine and evaluate it for negative theta, I get negative sine of theta. So if I have sine of negative 390 degrees, I can take that negative out of the argument and just move it out front. So this is equal to negative sine of 390 degrees. Well, we also know that sine is periodic, so we know that every 2 pi we're going to get the exact same value. So this is clearly more than 1 revolution. So we can subtract off 1 full revolution and we'll end up at the same point. And we'll end up with a point that's on our unit circle. So this is really negative sine of 390 degrees minus 360, 1 full revolution. So we get negative sine of, well, 390 minus 60 is 30. So if we can figure out what sine of 30 degrees is, we just make it negative and we have negative sine of 30. So let's go to our unit circle. We're looking for sine of 30. So this time let's draw our angle in, I don't know, green. We'll do green. It's a little bit hard to see, but I think we'll be able to do it. So we have an angle here. We've got our initial side on the x-axis. We're going to have our terminal side at 30 degrees. So we intersect the unit circle here. Remember, sine is the y coordinate, so sine is 1/2. But we're dealing with negative sine of 30 degrees, so we get negative 1/2. Okay? Now, finally, we have tangent of negative 37 pi over 4. We know that tangent is odd. So that means that we can take that negative in the argument and pull it out front because tangent of negative theta equals negative tangent of positive theta. So this is equal to negative tangent of 37 pi over 4. Okay? So hopefully that's not too bad. The next part's a little bit weird. So what we need to do is realize that tangent is periodic. Okay, we know that. And it has a period of pi. So we have a period of pi radians. Okay, so what I want to do, because I'm dealing with over 4, so I've got 37 pi over 4, let's rewrite this period with a denominator of 4. So I need to rewrite this as 4 pi over 4. 4 divided by 4 is really just 1, so I'm really just multiplying pi by 1, but it gives me a numerator or a denominator in this case that works. So I need to subtract off multiples of 4 pi over 4. Well, I've got 37 pi. I need to knock off multiples of 4 pi from that numerator. So basically what's happening here is I have negative tangent of 37 pi over 4, and I want to subtract off 9 full pi, okay? So that's 9 full periods of tangent, okay? Well, 9 pi is really 9 times 4 pi over 4, so that equals negative tangent of 37 pi over 4 minus 9 times really 4 pi over 4, so 36 pi over 4, which is negative tangent of pi over 4. So again, you probably don't have the unit circle memorized, so let's go take a peek. So on our unit circle, I'm going to erase some stuff because it's getting messy. I got most of it. Okay, so let's draw an angle of pi over 4 radians. Okay. So we have our vertex, our initial side. We intersect the unit circle at 45 degrees. Now remember, tangent is sine over cosine. Sine and cosine are the same thing here. They're root 2 over 2. So if I take a number and I divide it by exactly itself, I get 1. So what we're dealing with here is tangent of pi over 4 is just 1, but we have this negative. So this equals negative 1. Okay, so when you're dealing with radians, it's always much harder because you're dealing with all the fractions. Degrees, not bad. Radians, they take a little bit of work. So just keep practicing your work with fractions, okay? Two more quick examples. Hopefully they're quick. These videos, good Lord, this is a long section. Okay, example 12, without using a calculator, find the exact value of the following. We can do this two ways, okay? So we can use the idea of even and oddness of functions, or we can just sort of like work this out using our unit circle. Whatever is preferred is fine. So because we just learned about even and odd functions, that makes me kind of want to use even and odd functions. So when I have tangent, let's go over to the side. When I have tangent of negative 5 pi over 6, I can acknowledge that tangent is an odd function, which tells me that tangent of negative theta, we clearly have a negative theta here, equals negative tangent of that positive theta. So I could rewrite this as negative tangent of 5 pi over 6. Okay? Now we have this idea of reference angles, and we could use reference angles here, or we could just use our unit circle. Whatever is preferred is fine. I'm probably just going to use my unit circle for the sake of time. So let's rewrite this problem as negative tangent of 5 pi over 6 minus cotangent of 7 pi over 2. Okay? Well, let's go to the unit circle here. So let's look at tangent first. So we've got to look at tangent of 5 pi over 6. So let's go to our unit circle. 5 pi over 6 is one of the values on our unit circle. So let's see what that's going to look like. It is late, y'all. I am worn out. I'm telling you. Whew, it's been a long day. Okay, so we have our vertex, our initial side, and our terminal side is going to intersect right here. Okay, so we want tangent of 5 pi over 6. So we know that tangent is, let me use black here, tangent is sine over cosine. So that's going to be 1/2 divided by negative root 3 over 2. So let's kind of just work that out. So that's going to be 1/2 times 2 over negative root 3. Okay. So the 2's cancel, and I'm left with negative 1 over root 3. And I'm going to leave it like that for now. We can rationalize it in a bit. So we're just going to leave it as negative 1 over root 3 and see if anything simplifies out. Okay. So over here, let's go back to my worksheet. I had negative 1 over root 3. But I have this negative 2, okay? So what's happening there? Well, I have negative tangent of pi over 6, so I need to put a negative right here, which makes this 1 over root 3. So watch your signs, okay? Now let's address cotangent. Okay, cotangent we know is periodic and it has a period of pi. Okay, so we know we're dealing with pi over 2s. We've got this denominator of 2. So let's rewrite pi as 2 pi over 2. So that's still equal to pi. 2 over 2 is just 1. 1 times pi is pi. But now we have this denominator that we can work with. So let's think about cotangent of 7 pi over 2. We want to subtract off multiples of pi. So how many 2 pi's can I get out of 7 pi's? Well, 3. So I want to subtract off 3 pi. So cotangent of 7 pi over 2 minus 3 pi. But remember, we're writing pi now as 2 pi over 2. So that's going to be 2 times 3 pi, which is 6 pi over 2. So I get cotangent of pi over 2. Okay, so again, please get comfortable with fractions. I know sometimes I have to just zip through the fractions, and I hate that. My background is developmental education, where we show every little detail and we really walk through things. So it's hard to like not take the time to show you this, but really get comfortable with your fractions here, okay? And now we can go to our unit circle and we can look at pi over 2 as far as cotangent is concerned. So pi over 2 is right here, okay? So we know that cotangent is the reciprocal of tangent, and we know that tangent is sine over cosine. So cotangent is cosine over sine. We know that cosine is x and sine is y. So that's going to be 0 over 1 because this is our point right here. So that just equals 0. So cotangent of 7 pi over 2 is the same as cotangent of pi over 2, which is 0. Okay? So back to our problem. We have minus 0, so minus 0. So I get 1 over root 3, but I need to rationalize it. So I get root 3 over 3. So after a lot of work, we get the exact value of tangent of negative 5 pi over 6 minus cotangent of 7 pi over 2 is root 3 over 3. And finally, we are almost done with 7.5. It feels like we've been working on this for 142 hours, okay? It's really, 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 really late though. So that's probably why it feels that way for me. Okay, so for example 6, it says if f of x equals sine of x and f of a equals 2, find the exact value of the following. Well, we're just going to do a play on even and odd functions and then the periodic nature of sine, okay? So we know that f of x is sine of x, okay? We also know that if we evaluate that function at a, we get 2. Well, what would happen if we evaluated that function at negative a? Well, we know that sine is odd. So that tells me that sine of negative theta equals negative sine of theta. So if I have f of a equals 2, so that means sine evaluated at a equals 2, then f of negative a is going to equal negative 2. Okay? So because of the fact that sine is odd, we would say this equals negative 2. Okay? We just bring that negative out front, and then we get negative times f of a, so negative 2. Okay? Now, for part B, we're looking at the idea that sine is periodic. So we know that sine is periodic. And we know that the period is 2 pi. So we had this idea earlier that if we had f of theta and we added p, that would just equal f of theta as long as p represented our period. Okay, so I could take f of theta plus p, that would equal f of theta plus 2p, which would equal f of theta plus however many p, 3p, and so on, okay? Just remember what your period is. Well, for sine, the period is 2 pi. So if I take theta and I add or subtract multiples of 2 pi, I'm ending up right at the same spot because I'm just going all the way around the unit circle, either direction. So if I have f of a, we know that's 2, okay? So f of a we know is 2. F of a plus 2 pi is going to be the exact same thing because we're just going all the way around doing another revolution, so we're going to get the exact same value. So this is also 2, okay? And if I say I have f of a equals 2, but then I go around the circle, and then I go around the circle again, so I do 2 full revolutions, that would be 4 pi, that's going to put me right back where I started from. Okay, so I get f of 4 pi. So I really just get 2 plus 2 plus 2 equals 6. Okay, so that's one way that you can use function notation with this idea of even and odd functions, or the fact that the trigonometric functions are periodic. So again, this has been 167 hours now that we've been dealing with 7.5. This is a long section, y'all, so keep at it, keep working at it, you're kicking butt. Let me know in class if you have any questions, okay?